My name is Jacob Thomas, and my partner's name is Josh Dearborn. Our project began by Josh wondering why his heating bill was so high the last several months. Having learned many principles of heat transfer this semester, and being provided with the opportunity for a project, we determined it would be a great experience for us to apply what we've learned throughout this course. Apartments are very common throughout college towns, and Rexburg is no exception. We know the winters can be rough, and each student wants to save as much money as they can. Josh's apartment, as highlighted, will be the model we are going to use for our project. The purpose of our project was to determine the heat loss occurring within Josh's apartment. Like most apartments, Josh's consists of walls, windows, and a door. Through our studies of heat transfer, we believed we had been well equipped with the knowledge in order to calculate the heat loss in his apartment. We briefly designed a small 3D model of Josh's apartment and the surfaces which we would be using to observe heat loss. As you can see in this model, the two green surfaces are connected to neighboring apartments. One is a wall and the other is the floor. We decided that these surfaces would be treated as adiabatic due to their close relations to neighboring apartments at similar temperatures. We also would need to calculate the heat loss to the ceiling, attic, and roof as shown on the right. The conditions we assumed for this model were on a typical Rexburg day with winds of 20 miles per hour and temperatures of 47 degrees Fahrenheit. Before we began our calculations, we knew we would need to make several assumptions on material properties. We first assumed that the drywall values would be equivalent to those of gypsum board. Research showed that typical wood types used for studs were spruce, fir, and pine. Of those three, we decided to use the values of fir. The wood between and over the studs was assumed to be hardboard siding. The insulation in the wall was known to be paper-faced. Josh went into the attic and observed that it consisted of loose fill insulation. The roof was known to have black asphalt shingles. The two windows within Josh's apartment were double-paned with air in between them. The door was determined to have thin layers of plain carbon steel on the surface with a solid wood core assumed to be fir. The metal siding on the outside of the apartment was researched to be plain carbon steel. After determining the materials needed, we began looking up our key equations. Convection, conduction, and radiation were methods we wanted to use in order to calculate these losses. We began with a resistance model due to the difficulty of obtaining the temperatures within the walls. These equations were the basis of our resistance network. Our heat transfer coefficients were each determined based upon the Reynolds number being turbulent or laminar, and using the appropriate Nusselt correlations. Our model begins from inside the apartment and moves outward. This is our model for the walls. The windows, as mentioned, were double-paned. The door is shown next with its respective resistances. The ceiling and roof were also calculated using the resistances as shown. Doing research and speaking with professors, we learned that the air in the attic may need to be treated as air infiltration. Air infiltration can be defined as an uncontrolled inward leakage of air through cracks, spaces, and gaps in any building element caused by the pressure effects of wind or the effect of differences in the indoor and outdoor air density. Through the wind blowing in the vent and the temperature differences between the attic and outside, these led to some differences in pressure. Because this concept was new to us, we decided to make two models which hinged upon losses being in the attic, assumed as either convection or air infiltration. That one difference was calculated with the following equation. As mentioned previously, the difficulties in obtaining the internal temperatures led us to create resistance networks for each surface as shown. For the walls, windows, and door. The attic space was where our two models differed, with the top resistance network showing the convection, conduction, and radiation through and from the ceiling, attic, and roof, and the bottom network showing where the convection through the air was replaced with the heat loss due to infiltration. After running our calculations, it was found that the ceiling and largest exterior wall had the greatest amounts of heat loss, with 59.66 and 58.47 watts respectively. It was also calculated that the door and windows only lost 11.32 and 10.34 watts respectively. Our air infiltration model proved to dramatically affect the losses from the ceiling and through the roof with values as shown. The total heat loss calculated by our models without and with air infiltration were found to be 139.79 and 219.06 watts respectively. After completing our calculations, we wanted to take another step and observe Josh's apartment using a thermal imaging camera. By doing this, we would be able to observe some of the specific regions where heat losses were greatest. The blue lines in this first image are the studs which were in Josh's wall. It is easily observed how they are drawing much more heat away from the building compared to the drywall and insulation in between them. The second image shows there are large heat losses at the sides of the door and the base of the window. This image was very interesting to us because it shows the temperature differences in the attic. The blue are the attic supports, greenish yellow is the loose fill insulation, and the red is actually the plywood on the roof. We initially thought the insulation would be giving off more heat than the plywood, however the thermal image camera showed us the opposite. After doing more research, we learned that insulation is best when it is not subjected to convection. Airflow causes the insulation to lose its effectiveness and act as more of a filter than an insulator. This made sense due to its composition and the amount of air circulating in the attic. Lastly, this is a picture of the roof and shows us some significant heat losses as we had previously calculated. The purpose of this project was to determine the heat loss in Josh's apartment. We felt very confident that we had done this, and in the spirit of wanting to see how closely our model could match this apartment, we looked at his monthly heating bill. This graph shows the amount of usage Josh had over the last several months, as well as the average monthly temperatures. We averaged the last 4 months due to their fairly consistent behavior and compared them to our two models. After running several minor calculations, the model without air infiltration proved to be accurate within 1.74%, whereas the air infiltration model yielded a 54.0% error. We attributed the large disparity of our air infiltration model to our lack of understanding of the principles behind it. However, we are confident in our knowledge of conduction, convection, and radiation, and the assumptions we made for our model due to accuracy we achieved. Overall, we are very pleased with our results, and we're happy to see the principles we have learned in heat transfer could be applied to real-world scenarios and produce accurate results.